Now remember that the difference between deep learning and traditional machine learning and traditional AI was that deep learning will learn what the features are. And so here I want to highlight again why it's a very powerful thing to do to learn what the features are. And the reason is that it's often hard to say exactly what features we should use to solve our information processing problem. For example, take these two photos of older white men. Even if they weren't famous, we would all know that they're not the same person. But what visual features allowed us to know that? Is it the subtle shape difference in the nose? Is the difference in the slope of the forehead? It's very hard to say why we know these are not the same person. And this is why traditional machine learning had limited success on this type of natural problem like face recognition. But deep learning models are able to figure out what are the features that are most effective for distinguishing different faces. So we don't have to tell the deep learning model exactly what features to use. We can just put in a naive representation of face images, let's say of the pixels, and then let the deep learning model figure it out. Some problems we could solve about face image data include, who is this person? We could ask the model to tell us what is the emotion on this face. We could ask the model to tell us, is this person trustworthy? I want to talk a bit more about why using an appropriate feature representation is so important for intelligent information processing. To do so, I'm going to go back to talking a bit more about biological neural networks in our brains. In our first lecture, we had said how information processing was about finding relevant structure by narrowing down from a subset of a much larger set of possibilities. We went through a calculation showing that the number of possible different images in the world on a pixel-by-pixel basis was a number with at least 1 million zeros behind it, if not more. How are we able to do this? How is this done by the biological neural networks in our brains? Well, what our brains do is that we specialize, and we're very efficient about what we pay attention to. Our visual systems can't actually recognize all the possible images in the world. For example, we're not able to recognize this specific image of white noise from other images of white noise if we were to see it again. Instead, we only recognize images that have what we perceive as structure. Our visual system has evolved to specialize in processing images that correspond to objects in the real world that matter to our decision-making. It's possible that if recognizing different white noise patterns were key to our survival, we might have evolved to be able to recognize different images of white noise. But this wasn't the case. Our visual systems have evolved to detect objects, which is what matters to us. This specialization of our visual neurons for real-world objects is achieved through having neurons that detect basic features that are most efficient for describing the images we care about, which are objects like tigers and not white noise. Here is shown the response functions of some real biological neurons, retinal neurons, and neurons in the outer visual system. These were measured from non-human primates. What these response functions stand for is the image pattern that a single neuron will detect. So when a feature in an image matches the pattern in the response function for a given neuron, that neuron will activate and send a signal to all the other neurons that it's connected to, communicating that this visual pattern has been detected. We can see that many of these neural response functions have this pattern where there is a white strip in the middle and two darker strips on the side, all tilted with different orientations. The white strip surrounded by darker strip means that the visual pattern being detected is an edge, and the different orientations correspond to edges being detected at different angles. We see that these biological visual neurons are specialized to detect different types of edges that outline objects and object features. It turns out that if we train an artificial neural network to efficiently represent natural images, then we also come up with similar oriented dark and light strips for response functions of our artificial neurons. This is shown here on the right. These are the results of artificial neurons being trained to be efficient to represent a whole bunch of natural images, like scenes from a forest and trees and mountains and so on. And the resulting structure of these artificial neurons that have been given constraints to be efficient about representing these natural images look like the structure of our biological neurons in terms of having these orientation detectors. And when we train deep neural networks for our image processing tasks, the feature representations in the early layers of our artificial neural networks also tend to have these features of these differently oriented edge detectors. This is why we aren't able to process white noise, but we can recognize tigers in forests.